vacuum as space void of matter. The word stems from the Latin adjective vacuus for vacant or void. An approximation to such vacuum is a region with a gaseous pressure much less than atmospheric pressure. Physicists often discuss ideal test results that would occur in a perfect vacuum, which they sometimes simply call vacuum or free space, and use the term partial vacuum to refer to an actual imperfect vacuum as one might have in a laboratory or in space. In engineering and applied physics, on the other hand, vacuum refers to any space in which the pressure is lower than atmospheric pressure. The Latin term in vacuo is used to describe an object that is surrounded by a vacuum. The quality of a partial vacuum refers to how closely it approaches a perfect vacuum. Other things equal to lower gas pressure means higher quality vacuum. For example, a typical vacuum cleaner produces enough suction to reduce air pressure by around 20%. Much higher quality vacuums are possible. Ultra-high vacuum chambers, common in chemistry, physics, and engineering, operate below 1/1,000,000th of atmospheric pressure, and can reach around 100 particles per cc. Outer space is an even higher quality vacuum, with the equivalent of just a few hydrogen atoms per cubic meter on average. According to modern understanding, even if all matter could be removed from a volume, it would still not be empty, due to vacuum fluctuations, dark energy, transients, gamma rays, cosmic rays, neutrinos, and other phenomena in quantum physics. In the electromagnetism in the 19th century, vacuum was thought to be filled with a medium called ether. In modern particle physics, the vacuum state is considered the ground state of matter. Vacuum has been a frequent topic of philosophical debate since ancient Greek times, but was not studied empirically until the 17th century. Evangelista Torricelli produced the first laboratory vacuum in 1643, and other experimental techniques were developed as a result of his theories of atmospheric pressure. A Torricellian vacuum is created by filling a tall glass container closed at one end with mercury, and then inverting the container into a bowl to contain the mercury. Vacuum became a valuable industrial tool in the 20th century with the introduction of incandescent light bulbs and vacuum tubes, and a wide array of vacuum technology has since become available. A recent development of human spaceflight has raised interest in the impact of vacuum on human health, and on life forms in general. Etymology. The word vacuum comes from a Latin an empty space, void, noun use of neuter of vacuus, meaning empty, related to vacare, meaning be empty. Vacuum is one of the few words in the English language that contains two consecutive letters U. Historical interpretation. Historically, there has been much dispute over whether such a thing as a vacuum can exist. Ancient Greek philosophers debated the existence of a vacuum, or void, in the context of atomism, which posited void and atom as the fundamental explanatory elements of physics. Following Plato, even the abstract concept of a featureless void faced considerable skepticism. It could not be apprehended by the senses. It could not, itself, provide additional explanatory power beyond the physical volume with which it was commensurate, and by definition, it was quite literally nothing at all, which cannot rightly be said to exist. Aristotle believed that no void could occur naturally, because the denser surrounding material continuum would immediately fill any incipient rarity that might give rise to a void. In his Physics book IV, Aristotle offered numerous arguments against the void. For example, that motion through a medium which offered no impediment could continue ad infinitum, there being no reason that something would come to rest anywhere in particular. Although Lucretius argued for the existence existence of vacuum in the 1st century BC, and Hero of Alexandria tried unsuccessfully to create an artificial vacuum in the 1st century AD. It was European scholars such as Roger Bacon, Blasius of Parma and Walter Burley in the 13th and 14th century who focused considerable attention on these issues, eventually following Stoic physics in this instance. Scholars from the 14th century onward increasingly departed from the Aristotelian perspective in favor of a supernatural void beyond the confines of the cosmos itself, a conclusion widely acknowledged by the 17th century, which helped to segregate natural and theological concerns. Almost 2,000 years after Plato, René Descartes also proposed a geometrically based alternative theory of atomism, without the problematic nothing-everything dichotomy of void and atom. Although Descartes agreed with the contemporary position that a vacuum does not occur in nature, the success of his namesake coordinate system, and more implicitly, the spatial corporeal component of his metaphysics, would come to define the philosophically modern notion of empty space as a quantified extension of volume. By the ancient definition, however, directional information and magnitude were conceptually distinct, with the acquiescence of Cartesian mechanical philosophy to the brute fact of action at a distance and at length. Its successful reification by force fields and ever more sophisticated geometric structure, the anachronism of empty space widened until a seething ferment of quantum activity in the 20th century filled the vacuum with a virtual pleroma. The explanation of a clepsydra, a water clock, was a popular topic in the Middle Ages. Although a simple wineskin sufficed to demonstrate a partial vacuum, in principle, more advanced suction pumps had been developed in Roman Pompeii. In the medieval Middle Eastern world, the physicist and Islamic scholar Al-Farabi conducted a small experiment concerning the existence of vacuum, in which he investigated handheld plunges in water. He concluded that air's volume can expand to fill available space, and he suggested that the concept of perfect vacuum was incoherent. However, according to Nader el-Bizri, the physicist Ibn al-Haytham and the Mu'tazili theologians disagreed with Aristotle and al-Farabi, and they supported the existence of a void. Using geometry, Ibn al-Haytham mathematically demonstrated that places the imagined three-dimensional void between the inner surfaces of a containing body. According to Ahmad Dalal, Abu Rayhan al-Biruni also states that there is no observable evidence that rules out the possibility of vacuum. The suction pump later appeared in Europe from the 15th century. Medieval thought experiments into the idea of a vacuum considered whether a vacuum was present, if only for an instant, between two flat plates when they were rapidly separated. There was much discussion of whether the air moved in quickly enough as the plates were separated, or, as Walter Burley postulated, whether a celestial agent prevented the vacuum arising. The commonly held view that nature abhorred a vacuum was called horror vacui. Speculation that even God could not create a vacuum if he wanted to was shut down by the 1277 Paris condemnations of Bishop Etienne Tempier, which required there to be no restrictions on the powers of God, which led to the conclusion that God could create a vacuum if he so wished. Jean Burdon reported in the 14th century that teams of 10 horses could not pull open bellows when the port was sealed. The 17th century saw the first attempts to quantify measurements of partial vacuum. Evangelista Torricelli's mercury barometer of 1643 and Blaise Pascal's experiments both demonstrated a partial vacuum. In 1654, Otto von Guericke invented the first vacuum pump and conducted his famous Magdeburg hemispheres experiment, showing that teams of horses could not separate two hemispheres from which the air had been partially evacuated. Robert Boyle improved Guericke's design and with the help of Robert Hooke further developed vacuum pump technology. Thereafter, research into the partial vacuum lapsed until 1850, when August Toepler invented the Toepler pump and Heinrich Geissler invented the mercury displacement pump in 1855, achieving a partial vacuum of about 10 pascals. A number of electrical properties become observable at this vacuum level, which renewed interest in further research. While outer space provides the most rarefied example of a naturally occurring partial vacuum, the heavens were originally thought to be seamlessly filled by rigid indestructible material called ether. Borrowing somewhat from the pneuma of Stoic physics, ether came to be regarded as the rarefied air from which it took its name. Early theories of light posited a ubiquitous terrestrial and celestial medium through which light propagated. Additionally, the concept informed Isaac Newton's explanations of both refraction and of radiant heat. 19th-century experiments into this luminiferous ether attempted to detect a minute drag on the Earth's orbit. While the Earth does, in fact, move through a relatively dense medium in comparison to that of interstellar space, the drag is so minuscule that it could not be detected. In 1912, astronomer Henry Pickering commented, "While the interstellar absorbing medium may be simply the ether, is characteristic of a gas, and free gaseous molecules are certainly there." In 1930, Paul Dirac proposed a model of the vacuum as an infinite sea of particles possessing negative energy, called the Dirac sea. This theory helped refine the predictions of his earlier formulated Dirac equation, and successfully predicted the existence of the positron, confirmed 2 years later. Werner Heisenberg's uncertainty principle, formulated in 1927, predict a fundamental limit within which instantaneous position and momentum, or energy and time, can be measured. This has far-reaching consequences on the emptiness of space between particles. In the late 20th century, so-called virtual particles that arise spontaneously from empty space were confirmed. Quantum mechanics. In quantum mechanics and quantum field theory, the vacuum is defined as the state with the lowest possible energy. In quantum electrodynamics, this vacuum is referred to as QED vacuum, to distinguish it from the vacuum of quantum chromodynamics, denoted as QCD vacuum. QED vacuum is a state with no matter particles, and also no photons, is described above. This state is impossible to achieve experimentally. Nonetheless, it provides a good model for realizable vacuum, and agrees with a number of experimental observations as described next. QED vacuum has interesting and complex properties. In QED vacuum, the electric and magnetic fields have zero average values, but the variances are not zero. As a result, QED vacuum contains vacuum fluctuations, and a finite energy called vacuum energy. Vacuum fluctuations are an essential and ubiquitous part of quantum field theory. Some experimentally verified effects of vacuum fluctuations include spontaneous emission and the Lamb shift, Coulomb's law, and the electric potential in vacuum near an electric charge are modified. Theoretically, in QCD vacuum, multiple vacuum states can coexist. The starting and ending of cosmological inflation is thought to have arisen from transitions between different vacuum states, for theories obtained by quantization of a classical theory. Each stationary point of the energy in the configuration space gives rise to a single vacuum. String theory is believed to have a huge number of vacua, the so-called string theory landscape. Outer space. Outer space has very low density and pressure, and is the closest physical approximation of a perfect vacuum. But no vacuum is truly perfect. not even in interstellar space, where there are still a few hydrogen atoms per cubic meter. Stars, planets, and moons keep their atmospheres by gravitational attraction, and as such, atmospheres have no clearly delineated boundary. The density of atmospheric gas simply decreases with distance from the object. The Earth's atmospheric pressure drops to about 6,998,320,000,000 spadesuit 3.2 times 10⁻² pascals at 100 kilometers of altitude. The Kármán line, which is a common definition of the boundary with outer space. Beyond this line, isotropic gas pressure rapidly becomes insignificant when compared to radiation pressure from the Sun and the dynamic pressure of the solar winds. So the definition of pressure becomes difficult to interpret. The thermosphere in this range has large gradients of pressure, temperature, and composition, and varies greatly due to space weather. Astrophysicists prefer to use number density to describe these environments in units of particles per cubic centimeter. But although it meets the definition of outer space, the atmospheric density within the first few hundred kilometers above the Kármán line is still sufficient to produce significant drag on satellites. Most artificial satellites operate in this region, called low Earth orbit, and must fire their engines every few days to maintain orbit. The drag here is low enough that it could theoretically be overcome by radiation pressure on solar sails. A proposed propulsion system for interplanetary travel. Planets are too massive for the trajectories to be significantly affected by these forces, although their atmospheres are eroded by the solar winds. All of the observable universe is filled with large numbers of photons, the so-called cosmic background radiation, and quite likely a correspondingly large number of neutrinos. The current temperature of this radiation is about 3 K, or -270 degrees Celsius, or -454 degrees Fahrenheit. Measurement. The quality of a vacuum is indicated by the amount of matter remaining in the system, so that a high-quality vacuum is one with very little matter left in it. Vacuum is primarily measured by its absolute pressure, but a complete characterization requires further parameters, such as temperature and chemical composition. One of the most important parameters is the mean free path of residual gases, which indicates the average distance that molecules will travel between collisions with each other. As the gas density decreases, the MFP increases, and when the MFP is longer than the chamber, pump, spacecraft, or other objects present, the continuum assumptions of fluid mechanics do not apply. This vacuum state is called high vacuum, and the study of fluid flows in this regime is called particle gas dynamics. The MFP of air at atmospheric pressure is very short, 70 nanometers, but at 100 millipascals the MFP of room temperature air is roughly 100 millimeters, which is on the order of everyday objects such as vacuum tubes. The Crookes radiometer turns when the MFP is larger than the size of the vanes. Vacuum quality is subdivided into ranges according to the technology required to achieve it or measure it. These ranges do not have universally agreed definitions, but a typical distribution is shown in the following table. As we travel into orbit, outer space, and ultimately intergalactic space, the pressure varies by several orders of magnitude. Atmospheric pressure is variable but standardized at 101.325 kilopascals. Low vacuum, also called rough vacuum or coarse vacuum, is vacuum that can be achieved or measured with rudimentary equipment such as a vacuum cleaner and a liquid E-column manometer. Medium vacuum is vacuum that can be achieved with a single pump, but the pressure is too low to measure with a liquid or mechanical manometer. It can be measured with a McLeod gauge, thermal gauge, or a capacitive gauge. High vacuum is vacuum where the MFP of residual gases is longer than the size of the chamber or of the object under test. High vacuum usually requires multi-stage pumping and ion gauge measurement. Some texts differentiate between high vacuum and very high vacuum. Ultra-high vacuum requires baking the chamber to remove trace gases, and other special procedures. British and German standards define ultra-high vacuum as pressures below 10-6 pascals. Deep space is generally much more empty than any artificial vacuum. It may or may not meet the definition of high vacuum above, depending on what region of space and astronomical bodies are being considered. For example, the MFP of interplanetary space is smaller than the size of the solar system, but larger than small planets and moons. As a result, solar winds exhibit continuum flow on the scale of the solar system, but must be considered a bombardment of particles with respect to the Earth and Moon. Perfect vacuum is an ideal state of no particles at all. It cannot be achieved in a laboratory, although there may be small volumes which, for a brief moment, happen to have no particles of matter in them. Even if all particles of matter were removed, there would still be photons and gravitons, as well as dark energy, virtual particles, and other aspects of the quantum vacuum. Hard vacuum and soft vacuum are terms that are defined with a dividing line defined differently by different sources, such as 1 torr or 0.1 torr. The common denominator being that a hard vacuum is a higher vacuum than a soft one. Relative versus absolute measurement. The vacuum is measured in units of pressure, typically as a subtraction relative to ambient atmospheric pressure on Earth, but the amount of relative measurable vacuum varies with local conditions. On the surface of Jupiter, where ground-level atmospheric pressure is much higher than on Earth, much higher relative vacuum readings would be possible. On the surface of the Moon, with almost no atmosphere, it would be extremely difficult to create a measurable vacuum relative to the local environment. Similarly, much higher than normal relative vacuum readings are possible deep in the Earth's ocean. A submarine maintaining an internal pressure of 1 atmosphere submerged to a depth of 10 atmospheres is effectively a vacuum chamber keeping out the crushing exterior water pressures, though the 1 atmosphere inside the submarine would not normally be considered a vacuum. Therefore, to properly understand the following discussions of vacuum measurement, it is important that the reader assumes the relative measurements are being done on Earth at sea level, at exactly 1 atmosphere of ambient atmospheric pressure. Measurements relative to 1 atmosphere. The SI unit of pressure is the pascal, but vacuum is often measured in torrs, named for Torricelli, an early Italian physicist. A torr is equal to the displacement of a millimeter of mercury in a manometer, with 1 torr equaling 133.322368 pascals above absolute zero. Pressure. Vacuum is often also measured on the barometric scale or as a percentage of atmospheric pressure in bars or atmospheres. Low vacuum is often measured in millimeters of mercury or pascals below standard atmospheric pressure. Below atmospheric means that the absolute pressure is equal to the current atmospheric pressure. In other words, most low vacuum gauges that read, for example, 50.79 torr. Many inexpensive low vacuum gauges have a margin of error and may report a vacuum of 0 torr, but in practice this generally requires a 2-stage rotary vane or other medium type of vacuum pump to go much beyond 1 torr. Measuring instruments. Many devices are used to measure the pressure in a vacuum, depending on what range of vacuum is needed. Hydrostatic gauges consist of a vertical column of liquid in a tube whose ends are exposed to different pressures. The column will rise or fall until its weight is in equilibrium with the pressure differential between the two ends of the tube. The simplest design is a closed-end U-shaped tube, one side of which is connected to the region of interest. Any fluid can be used, but mercury is preferred for its high density and low vapor pressure. Simple hydrostatic gauges can measure pressures ranging from 1 torr to above atmospheric. An important variation is the McLeod gauge, which isolates a known volume of vacuum and compresses it to multiply the height variation of the liquid column. The McLeod gauge can measure vacuums as high as 10⁻⁶ torr, which is the lowest direct measurement of pressure that is possible with current technology. Other vacuum gauges can measure lower pressures, but only indirectly by measurement of other pressure-controlled properties. These indirect measurements must be calibrated via a direct measurement, most commonly a McLeod gauge. The kinetometer is a particular type of hydrostatic gauge, typically used in power plants using steam turbines. The kinetometer measures the vacuum in the steam space of the condenser, that is, the exhaust of the last stage of the turbine. Mechanical or elastic gauges depend on a Bourdon tube, diaphragm, or capsule, usually made of metal, which will change shape in response to the pressure of the region in question. A variation on this idea is the capacitance manometer, in which the diaphragm makes up a part of a capacitor. A change in pressure leads to the flexure of the diaphragm, which results in a change in capacitance. These gauges are effective from 103 torr to 10⁻⁴ torr and beyond. Thermal conductivity gauges rely on the fact that the ability of a gas to conduct heat decreases with pressure. In this type of gauge, a wire filament is heated by running current through it. A thermocoupler resistance temperature detector can then be used to measure the temperature of the filament. This temperature is dependent on the rate at which the filament loses heat to the surrounding gas, and therefore on the thermal conductivity. A common variant is the Pirani gauge, which uses a single platinum filament as both the heated element and RTD. These gauges are accurate from 10 torr to 10⁻³ torr, but they are sensitive to the chemical composition of the gases being measured. Ion gauges are used in ultra-high vacuum. They come in two types, hot cathode and cold cathode. In the hot cathode version, an electrically heated filament produces an electron beam. The electrons travel through the gauge and ionize gas molecules around them. The resulting ions are collected at a negative electrode. The current depends on the number of ions, which depends on the pressure in the gauge. Hot cathode gauges are accurate from 10⁻³ torr to 10⁻⁻n torr. The principle behind cold cathode version is the same, except that electrons are produced in a discharge created by a high-voltage electrical discharge. Cold cathode gauges are accurate from 10⁻² torr to 10⁻⁹ torr. Ionization gauge calibration is very sensitive to construction geometry, chemical composition of gases being measured, corrosion and surface deposits. The calibration can be invalidated by activation at atmospheric pressure or low vacuum. The composition of gases at high vacuums will usually be unpredictable, so a mass spectrometer must be used in conjunction with the ionization gauge for accurate measurement.